rather than, I mean, homology of symmetric groups is a topic that I think would need no further motivation, but I felt like there were some nice threads to work through now. So let me talk about, I said some of them in the announcement email, but actually I neglected one. So let's say what the main theorems are. Let's call them the central theorems. In iterated loop space theory. So not to be confused with central limit theorems or anything like that. First, and we're going to have to define what this means, but something called the disk operad acts on an infold loop space. That implies that the homology of this operad acts, and let me sort of item 2.5 is, by this we mean both non-equivariant and equivariant. And the equivariant action is what's the remarkable connection, the deep connection between homotopy theory, in particular stable homotopy theory, or especially the interplay between stable and unstable homotopy theory. That love affair with the symmetric groups is contained in this, or is a big part of this equivariant action. Then we have the recognition theorem. If this operad acts on Y, and well, acting on Y means that pi naught is a monoid, but this is a group, then Y is homotopy equivalent to loops in on X for some X. Sorry, let me move this over, make it a little smaller. And then finally, and so this I forget, let me see if Jim Stasheff is here or not. Jim, are you here? You can speak up. Phew, because now I'm really, speaking about characteristic classes, that was, as he said, that was really Milner, and he was taking notes. I will believe him there, but this theorem 3 is very much his theorem. And then theorem 4 is that, in fact, that also, if I look at the infold loops on an infold suspension of some space, this is going to be the free disks in object module space on sort of the generators, but we have to group complete. Oops. And we'll say what that means, but that's basically take loops on the classifying space of a monoid. So, so yeah, let's review what these then mean in the first example, and there's some nice theorems to quote unquote recall. It might be new for some. So let's talk about the n=1 case of all of these. What we're going to see is that well, we'll state it. I don't know if we can say we'll see it, but disks 1 is equivalent to an operad called A infinity. and we'll see that in more detail. But the statement one that it acts, let's just, and again, I haven't defined acts, but part of this is just to get ready to define that action. So if I've got, so what is disks one? This is a space whose elements are little intervals inside an interval, and they don't have to occur in order. So it's just some subset of a cube, if you will. And then this acts means that I've got a map from here to, in this case, it would be, say, loops 3x, sorry, loops x cubed. And by the way, let me make sure I've got the chat up. Just in case. Just in case there's any questions or mistakes, like I didn't quite make. But I've got 3 loops, so they're just, call them, gamma 1, gamma 2, and gamma 3. And all I'm going to do is make a new loop, which for the times in green will be at the base point of x. So that's at base point. And then the times in blue, I'm going to apply gamma 1. I'll get a loop. I'll end up at the base point. I'll stay there for the times in that interval between 1 and 3, and so forth. And then I've got gamma 3 is the third one. This is just to be consistent across the different n. If all you cared about were single loop spaces, you could forego this formality and just assume that you're going to plug them in the order they come. So, that is sort of establishes 1 for n equals 1. And what that really means is, so then the consequence is that the homology of loops is an associative algebra. Yeah, because for this 3 case, you can see that this makes the concatenation product homotopy associative. So that means the homology is an associative algebra. And that's sort of the non-equivariant homology version of the operad acting. The equivariant, I'll just say there's no real equivariant. Well, there is one, but it gives nothing new. Here for n equals 1. 3, and we'll talk about this theorem. And again, this is due to Jim Stasheff. If this A infinity operad acts on some y and pi naught y is a group, then y is equivalent to loops x for some x. So that's Stasheff's recognition theorem. And then there's a theorem of James, which actually predates Stasheff's, which is illustrating 4 in this case. So if I've got a space, and I'm going to be based the whole time today, so if I neglect to mention it, assume that we're in the base category. So there's a way that I can map x to loop suspension x. If you will, it's the adjoint of the identity map. You'll see what I mean in a second. But because of that, there's an extension from x to the free monoid on x, again with this choice of base point. So what do I mean by that free monoid? Let me do some scrolling. What do I mean by that free monoid? Well, it's just this union. I'm going to take x. I'm going to have x cross x, x cubed. And then what we're going to do is, if I've got some x1, something in which the base point occurs, I guess I already called that the base point, then that's going to be identified with what we got, what we get when we omit it. And if you think about a free monoid on a pointed set, you're going to use that point for the identity. That's what you would kind of mean, the free monoid on a pointed set. And then this is exactly, multiplication by the identity should act as an identity. So this is a space you can make it. It should feel somewhat like the classifying space in these kinds of identifications. And then because loops on X, if you use more loops, it is a monoid, you get a map like that. And then James, so we're going to use a strict model rather than the A infinity model. And then James' theorem says that this is an equivalence. And the significance, I mean, there's a few different ideas of significance here. And by the way, before I forget, this is proven in Alan Hatcher's algebraic topology in an appendix, as well as many other places. I mean, this loop sigma, I think of it as a sort of, it's infinite dimensional, it's homogeneous. It's something that would be hard to, for example, put a cell structure on, whereas this is this is filtered by finite complexes. In fact, the corollary is that of things as I've stated it, the implication here is that the homology of loop sigma x, again, by James's theorem, that's the homology of this free monoid on X. And that's something that you can just calculate using the Kuhn theorem again and again. Let's assume with a field coefficient. So let's truly use Kuhn and with field coefficients. And that's something that you could just call to be consistent with what we might want to say later, the free associative algebra. It also, and that's just generated by this vector space, the reduced homology of X. But then that's also sometimes called the tensor algebra. For just historical reasons. So let me say a little bit about a little bit more about this. Let's pause here because this is, so again, there are plenty of proofs out there, and the proofs usually proofs start with this homology calculation. Calculate this and then deduce the theorem. That's the standard kind of proof. But let me say I'll just call it a wishful proof. In the spirit of these lectures. So there's no math here, but let me just say that I wish there were the following proof. So what is right? I didn't actually give the map. I better if, so what is the map? From this free monoid on X to loops suspension X. Well, I'm just going to take this list and I'm going to make, so we're going to use the reduced suspension. So that means all of this is identified with the base point. And here's X in the middle. And I've got X1, X2, etc. So for each of these points in this list, I'm going to make a loop in suspension that just goes down first through X1 and then through X2. It's sort of constant on the X coordinate. If I think of the suspension as the quotient of the product, it's constant on the X coordinate and then say constant time on the T coordinate just to be definite. And I can just keep on doing this because once I'm down at the bottom by the identifications, I'm up at the top again. So that's the map here. And the wishful proof, and you'd only expect this to get that this is a weak equivalence, but that's that actually then gives the full result because any mapping space between CW complexes has the homotopy type of a CW complex. I forget whether that was Milner or James or someone else. The wishful proof of weak equivalence would be to say, well, if I've got some SK to loops sigma X, could I retract it? So could I find a factorization through the monoids, the monoid on X? And the idea would be, well, in using compactness, you would then see if you could do the following thing, which you can obviously do for a single loop. So a single loop in this space, and you'd probably want to use some smooth approximation, smooth on the T coordinate at least. A single loop kind of winds around in the cone and then maybe passes or maybe doesn't. Eventually comes back to the base point. And in this case, I would say it should be the constant. Whereas if I have a loop that kind of meanders somehow and goes up to down, I would take one crossing point and you can imagine a retraction. And there's, let me draw the picture here. It's kind of like in the some proofs of the Freudenthal theorem, where you take the crossing in the middle, and then there could be lots of ugliness. So the one base case is that I do cross nicely in the middle and then go through. But this is homotopic to something where the ugly bits are pushed to the ends. And then eventually, for that portion of the loop, I get a constant on the X coordinate. And so the idea would be to retract onto these loops, which piecewise were constant on the X coordinate, using this idea of taking the crossing, say, at the middle and kind of quote unquote slurping things up or smoothing things up. You imagine your fingers on that middle portion. So anyways, let's see. So what else do we want to say here? Right, so let's now give some definitions. Navigate and give myself some space. Sorry, pressed a button that I shouldn't have. Let me get queued up. Okay, great. So as promised, let me give some definitions. First, before I even define an operad, let's just, the easiest definition in front of us is this disks D object. It's a collection of spaces, one for every, depends on what category exactly you want to work in, but every non-negative integer. And this is just a space, disk Dn is a space whose elements are collections of disks. Oh, shoot. Let me do one thing. There's a linear transformation here to manage all the time, and I did not apply it appropriately on the other end, so I was expecting something differently. So definitions. So disks in dimension D, the nth entry of that operad is this collection of, it's a space where a point in the space is a collection of disks, and that's just some subspace I won't bother writing out, but it's a subspace of, well, I've got the centers, which are points in the disks, and the radii, oops. So these are centers and radii, and you just topologize it as a subspace. Okay. Then I talked about operad actions, so we have to talk about that a little bit. And I'm not going to write out the definition of an operad. I will point out some places in the notes, but I will try to make it clear what that definition must be. So operads act, I won't tell you what they are, but they act to define algebraic structures on top of symmetric monoidal ones. And the analogy I want to make here is that groups act to define symmetries. Zoom out a little bit more. There we go. And so let me use this dictionary. Well, so what's a prototypical example? Would be all symmetries of some object that I care about. I'm thinking categorically. So just the automorphisms, the invertible morphisms from an object to itself. And then you see that you've got associativity, identity, and all that jazz. And what's the proto example in this case? In the operad setting, the proto example is called end, and I'll write it as if we're in some linear category. So end V, where end V N, let me just go ahead and say that, is just all maps from, I'm going to use a symmetric monoidal product, V to the N into V. Okay, and in fact, this actually carries a nice immediate. So a group action is just a map from some other group. So let me, from some other group to on X. That's an action on X. And here, the action is going to be a map from our operad O to this end V. And then if we unpack what you mean by a group action, well, using some adjointness, that means that we've got, if I have a map from G to odd X, it really means we've got a map from G cross X into X. And there'll be some axioms around that. And here what that means, in the operad land, it means that I've got something from the nth entry of the operad. Tensor, so my element of endomorphisms, again, I'm going to use some adjointness. Tensor V to the N to V. So an operad acts by taking a bunch of elements of V and producing another one, and which element you produce in V depends on the element of the operad. So what's probably my favorite example, and this has surprising, comes up a lot in topology actually. Although I won't give the topological version, we won't do spectral Lie algebras, at least this week, maybe if this lasts for a year or something. Anyone who wants to learn about spectral Lie algebras, by the way, the electronic computational homotopy theory seminar, which is open, is having a talk on that tomorrow. Okay, so, but we're going to be much more pedestrian. C is going to be the category of vector spaces over some field. Our symmetric monoidal product is going to be the usual one. And then this operad Lie, well, so what we want is, what you want to think about is Lie N, tensor V to the N, goes to V is our action. And that's going to be equivalent to having a Lie algebra structure. And so, so, you know, let's let n equals 3. If I have 3 vectors and I tell you to Lie multiply them, you should look back at me and say, well, I don't, you know, you're not giving me a well-defined task. You haven't told me how I want to Lie multiply them. There would be multiple ways to Lie multiply 3 things. And then I could, for example, pass along, well, I want you to multiply them this way. And you say, oh, okay, well, I'll just, since I've got a Lie algebra, that means I can take the bracket of V1 and V2 and then bracket that with V3, right? So that's what Lie multiplying 3 things, that's the additional data to Lie multiply 3 things. And what operads in general are additional data you need to multiply something for a particular algebraic structure. So conversely, if we have, so let the n be, I'm going to take the linear span of all bracket expressions on in letters, but I'm going to then quotient by anti-symmetry of the bracket and the Jacobi identity. And this should sound vaguely familiar from some of our discussions of configuration spaces. So then to give, so conversely, if Lee acts on V, then use the bracket Lee 2, which is, by the way, isomorphic to the ground field. It's generated by x1 bracket x2 or x2 bracket x1. So anyways, tensor V to define the bracket, and then check that we've set this up, that higher brackets are compatible. Not higher brackets in the further brackets, I should say, because higher brackets, people will think that we're doing L infinity. Further or deeper brackets are compatible. Okay, so that's Lee as an example. So I haven't defined an operad, but it's a collection of spaces. They're equipped to have maps with the products, with the algebras that they're acting on. And what you have to do to be compatible is that, for example, there's a way to take a twofold bracket, another twofold bracket, and there's for example, if I'll call it circ2, if I take x1, x2 cross, I don't know, x2, x1 to be tricky, this is sort of insert, if I insert x1, x2 into x2, x1, then I'm going to have x2, x3 bracket x1. So this this expression is what I put my x1, x2, quote unquote, into x2, and then I re-index the variables. And this is just a way to say, oh, okay, if I've got a way to multiply two things and another way to multiply two things, that can make a way to multiply three things, and that's the essential part of the operad axioms. Okay, I'm going to switch the boards now. Let me again apply the linear transformation. That makes this a bit easier. And then I'll erase this and go. So our next example, and this is one of the easiest parts of the whole story, is that disks, I guess I was using D now because I use N for the entries, acts on the default loops on X. And this is, yeah, just one of the simplest stories. If I have a disk with K entries, and then I start with K loops, and I think of each of these loops as a map from the D disk modulo its boundary to X. Then what I can do is make a new loop by applying my F1 at the place where the first disk was, and my F2 the place where the second disk was, and so on. And then what happens is, just as before in the one loop case, all this green is going to go to the base point of X. So I make a new loop by multiplying. And, you know, some of the history, I really sort of trace this back to, so compare with the proof, the standard proof that pi 2 of X is abelian, we could say that that really means that that's going to be implied by the space of sort of choices of multiplication on loops 2x is connected. And really, we're just using not the full space, whatever that would be, but just the subspace that's equivalent to the disks. Okay, so we've got that action, but now we can apply. But the point is that the whole point of the theory then is, well, one point of the theory is that if we apply homology with field coefficients and then the Kuhn theorem everywhere, then a topological operad acting implies that its homology acts on the homology of the space. And then what we're going to see is that the homology of the disks acts on homology loops dx. But this from the catch-up lecture is this Poisson operad. Let me remind you about how this isomorphism goes. The Poisson operad, if I use the language that I just used from the Lie operad, the Poisson operad has entries, for example, so this is just going to be an example again. The Poisson operad, you can bracket things and you can multiply them. Or I guess I did 6 here, x3. This homology class is going to be the following family of disks. I'm going to have one, oops, let me do this. I can use color. So I'm going to have the disk labeled 1 orbiting the center of mass of disks labeled 2 and 5. Oops. 2 and 5. And then it's 4 and 5. Try one more time. And then I'm going to have, pick another place somewhere, and 2 and 6 are orbiting one another. And then 3 doesn't move. It's constant the whole time. So I've got this, the degree is going to be, well, you give me 3 elements of 3 unit circles, 3 elements of the unit sphere in dimension d, so that's 3d minus 1, 3 times d minus 1, then we've got such a disk. So this is the significance, one of the significances of that calculation that I gave in the catch-up lecture, or not fully gave, but indicated in the catch-up lecture, that the homology of the disks operad is the Poisson operad. Let me make a remark. So intuitively, this is pretty clear. And the basic operad insertion is not hard. is relatively easy. So if I have, you know, we said with Lee, but so, you know, let's just, in general, if I'm thinking about O2 cross O2 to O3, and I'm inserting, so I've got like X1, X2, I can use the same. Lee is a suboperad, if you will, sort of up to the graded Lee in that degree. So if I'm inserting this in 2, so this means I've got the points 1 and 2 are orbiting. This also would be points 1 and 2 are orbiting, but I would call them 2 and 3 if I were inserting them into so if I insert them into 2 here, that means I'm going to call this 2 and call that 3, and this sort of becomes an orbiting picture down there. So the operad insertion is easy. What's actually not so easy in all of this is that, although again, it seems intuitively clear enough, is that insertion, so let me call that basic operad insertion before, not so easy is that, for example, x1 bracket x2 star x3, if I insert a product, then I should get, I didn't work out all the signs because it does depend on D, etc., but I should get something times x1 bracket x3, and then plus or minus x1 bracket x2 times x3. That's what a Poisson algebra is. And then the fun thing is that it's actually, to me anyways, the proof I found easier to establish these kinds of compatibilities in cohomology and use the perfect pairing between homology and cohomology. If you care about sort of full detail proofs and sort of not hand waving that this looks the same as that. All right. So let me give an example of the fourth statement then. So an example of the central theorem part 4 is that, and this is, or actually no, part 2, right? Oh no, part 4 is that the homology of loops in sigma n x with rational coefficients is isomorphic to the free graded Poisson algebra on the reduced homology of X. And let me make that clear that this sort of tells you everything. So, but let me let's see. Let's do it algebraically first, and then let me remind you what that operad action would be. Let's see. Right. Yes, Pedro, you could write that homotopy explicitly. Yeah, but it's actually it depends on what you have on hand. But I found that the cohomology statement was sort of true on the cochain level, basically, and so felt a bit cleaner. Right. So let's do an example of the example so that if I wanted to be concrete, suppose I look at maps from a 3-sphere to wedge of a 5-sphere and a 6-sphere. Then in degrees, 2 and 3, I have the sort of the adjoints of the inclusions of the 5-sphere and the 6-sphere. So let's call those x, or x sub 2, y sub 3. I'll just call them x and y. Then in degree 5, we have the product. In degree 7, we have, for example, x squared y is a perfectly good thing, but there's also x bracket y starting in that degree. In degree 8, you don't have xy squared because y is in odd degrees. You do have y bracket y though, because y is in odd degrees. The grading conventions work out for that, and you can keep on going. So this gives a complete calculation in the rational setting of some homology of these spaces. And let me again remind us then of the action. So what is the star and the bracket? So if I've got some, and this doesn't have to be a, so I'm going to think of a homology class as I'm going to take the union of the simplices that define its chains and then identify them when they're according to pairs. Do I have a good description of cohomology? I wouldn't say better any better than basically saying the dual of this. The cohomology in, I will say that I'm writing it up with Lorenzo Guerra and Paolo Salvadore, that we let n equals infinity and play with cohomology. We've got a better description, or a different description, a very distinct description from homology. And that's not over Q. So by the way, over Q here, I meant to say one other thing about this to note, that this is just the free commutative algebra. And that ends up being all you see. And that's the answer for the cohomology, or the homology still, of loops infinity, sigma infinity, x with rational coefficients. Not that we've talked a lot about why we care about that particular calculation, but over the rationals, the story is very simple. You just take the homology of x reduced and look at the free commutative algebra on that. That's the same answer you get from like SP infinity as well. But let me make sure that we're, with such calculation, we know that this is so if I've got a map from some kind of pseudo-manifold, some union of simplices, that's whose quote unquote fundamental class is representing a homology class, and another so let's say they represent two classes in the homology of this loop space. Then what I can do is then take, so what is the product? Well, I'm going to just take W cross V, two loops cross loops, and then multiply. So that's the standard Pontryagin product in homology, in the homology of the Lie group, but it's true in the homology of iterated loop spaces as well. But then what you can do, what about, oh, this is poor notation, I realize now. What about this bracket? Well, what I can do is for every choice of how to multiply, so you think about the all relative positions of 1 and 2 there, they give me a different way to multiply the quote unquote loop sum, the sphere sum. And then I can just take that and still end up getting, so that first naturally maps to disks 2 cross loops, and then I can use the operand action and I end up in the loop space, and this composite represents the bracket of those two homology classes, which unfortunately I've also used brackets to denote. So this is why you have these two algebraic structures, and then rationally it is a lovely story that tells the whole thing. Right. I have to decide now if it's worth doing much more, given that I won't say as much about the recognition theorem as I wanted to. You know, I think I might just call it a little bit early. I think that's good advice in general. What I will talk about next is then define the Fulton MacPherson operad. It's a different model for this disks operad, fairly different geometric flavor, although I won't prove that they're equivalent. That's a theorem of my good friend Paolo Salvatore. We'll have the Lashof polytope come up. We'll give almost a full proof of Lashof's recognition theorem, and I'll talk about the recognition theorem in general. And then maybe I'll talk about the equivariant operations a little bit as well. So I think this gets us to a good place. So I will sort of recap. So next time we'll talk about the Fulton MacPherson operad, which is another model for the same homotopy type. We'll talk about the recognition theorem, and then I'll discuss Dyer-Lashof operations, which is that equivariant piece of the story. So, and then that will segue into maybe we'll see, because a bit of the homology and cohomology of symmetric groups. Probably a little bit of it, but not very much. Okay, we'll call that a few minutes early. Questions that people want to ask publicly now, you can share them now. Otherwise, then I will stop the Zoom. Not the Zoom, the YouTube. Pretty clear, I hope. Not as much chatting today, but again, hopefully it's clear. And I've got some writing I've done on these topics, so I'll make sure that I link to those. Okay, I'm gonna